Welcome everyone. Thank you for joining us today. I'm happy to introduce today's webinar on adventures, misadventures in hybrid programming. Before we dive in, let's go over a few housekeeping items. Please keep your microphones muted during the presentation to avoid any background noise. Feel free to use the chat function to ask questions or share your thoughts. We'll have a dedicated Q&A session at the end where we'll address as many questions as possible. And this session is being recorded. The recording we will share with you afterwards on the ARCHER2 training page. Now let's get started. I'm delighted to introduce today's speaker, Kevin Stratford, who is a senior research fellow at EPCC. Kevin worked on an ARCHER2 ECSC project that involved Ludwig, a lattice Boltzmann code aimed at complex fluids. Kevin, the floor is yours.
Thanks, Juan. I'll switch the microphone on to get started. Perhaps somebody just could confirm their hearing. Okay.
Yep.
So thank you everybody for coming. As Juan has said, this work resulted from an ECSE project which ran sometime back in, started in 2020. So if my memory is growing slightly dim, that will be my excuse. So the title was here. I put this in, I think it may be more misadventures than adventures, and I try to include these things as it's often the things that go wrong or don't work that actually provide interest rather than just everything is fantastic. So here we go. So as I've said, this is going to be hybrid programming. I'll probably just like to say at the start a little bit about what I mean by hybrid programming. The context, as Juan said, is we have a code developed here at Edinburgh with the physics department over a number of years, and this is a lattice Boltzmann code for hydrodynamics, and with a specific slant, we like to look at complex fluids. So I'll just say a little bit about what those are. I'll say a little bit about how we do the abstraction for the shared memory model in the context of OpenMP for CPU computing, and also I'm going to take a broad view of what I mean by shared memory here to include GPU programming as well. I've got a few slides on the performance in terms of really looking at the kernels, but then also what I've termed hybrid performance here, and this is really the interaction between MPI and OpenMP in the context of ARCHER2. And just to try to be at least a little topical, I have a few results from a previous capability day, which is the ARCHER2 program to try out large scaling runs. I'll try to perhaps remember as we go through to stop at appropriate points to see if there are any questions, but I can see the chat as we go along. Okay, so as I said, I'm taking a broad view of hybrid programming here, or shared memory programming. So once upon a time, doing parallel programming, one thought about having a single MPI process associated with a single core, and that is indeed a model that is still present in some cases, but this evolved into one where one typically would like to have a single MPI process associated with many cores. Now, there may be various reasons for doing this. In the single MPI process per core, you have perhaps the replicated overheads of the MPI machinery in terms of memory. If you're running on a very many core system, you perhaps don't want to replicate that more than necessary. And the many core model, one typically thinks, certainly in terms of ARCHER2, is generally going to be OpenMP. But I include here a hybrid to include GPUs. And while there are various models you can think of about how you associate MPI processes with GPUs on a GPU machine, I'm just going to take the most simple view here, where we associate a single MPI process with a single GPU. Of course, the whole for the most recent GPU architectures, the whole idea of what represents shared memory programming is becoming more complex, as there is now a coherent view of host memory and device memory, if you're familiar with the GPU jargon in the latest architectures. Just a word on context. We have this code Ludwig, which takes its name from Ludwig Boltzmann, and we are trying to address problems in typically complex fluids with this code. So these are broadly mesoscale problems where you have a fluid, but you have typically something else introducing some extra physics. This might be a mixture of fluids with interfaces, or it may be a fluid particle, solid particle suspension. The example we're looking at today is also liquid crystals, which we'll say a little about. And there's also code for electrokinetics, which is broadly a fluid carrying charge. So this code does quite a lot of things, but I'll try and just stick to a fairly broad description here. So this is quite a code with quite a long history. It's basically ANSI C and is always used message passing for the distributed memory component. In about 2009, 2010, something like that, a colleague of mine, Alan Gray, started thinking about developing a GPU version. So at that time, the go-to model was CUDA, but we realized after some time we really wanted some degree of abstraction. So I'll say a little about what the abstraction is later on. The fluid part is basically isothermal incompressible Navier-Stokes, which are over there on the left. So if you're not familiar with this lattice Boltzmann picture, briefly, it comes from the microscopic picture of the Boltzmann equation, and is essentially a discretized form of the Boltzmann equation with a discretized velocity space. Computationally, the trick here is that one relaxes the constraint that the fluid is completely incompressible and allows a finite speed of sound. Computationally, this means you don't have to do some sort of global problem for the pressure, and the algorithm is local. So you only need, here's a picture here, you need nearest neighbor communication between subdomains. So that's the trick there. The price you pay in doing this is, in some sense, the time step becomes small compared with some characteristic time you're looking at in the problem. That's the name. This picture has a solid particle in. If you're doing particles, you get a completely resolved hydrodynamic interaction at the solid fluid surface. So just a word on the liquid crystal bit. So these are the particular benchmarks I'm going to show. So one has the fluid flow here, and what we do is have a coarse-grained picture in which there is an order parameter which lives on the same discrete regular lattice as the velocity and the density, etc. So the picture of the liquid crystal in the microscopic picture over on the left is you have something like rod-like molecules which have collectively elastic forces between them. So the bend and the twist of the rods imparts a stress on the fluid, and any shear in the fluid will tend to try and rotate the rods. So this microscopic picture is coarse-grained here into a picture where you have an order parameter which happens to have 5 independent components. Perhaps just going back to the previous slide, the other point I should make about the lattice Boltzmann, this discrete velocity set business means you have some 19 or 27 double precision floating point numbers living at each lattice site to represent the fluid quantities. So that's in some sense a slightly large memory requirement compared with the 10 hydrodynamic quantities you've got in 3 dimensions. So there's another 5 double precision floating point variables coming in to represent this order. So the interesting thing about liquid crystals, of course, are their optical properties. These arise from the sort of a large-scale defect superstructure in liquid crystals. So the interesting optical properties have occur at wavelengths in the visible. So those are you get some interesting optical properties. So here, this picture here is just has a liquid crystal with actually some spherical particles in it, and they've stuck it between cross polarizers here. You see these interference fringes where light is being blocked or transmitted through the and again, if you have this picture on the right is just a liquid crystal emulsion, I think, with the orientation is scattering different colors from different droplets, I think is that one. Okay, any questions so far? Hopefully that's so yes, perhaps the last thing to say about this liquid, incidentally the equations are truly horrific, so I'm not going to go into that. The upshot is we have also a nearest neighbor halo swap problem associated with these equations, which are just solved by finite difference with a halo extent which may be the same as or slightly greater than needed for the lattice Boltzmann. Okay, so I mentioned this business of how we wanted an abstraction which would allow us to run both on GPU systems and CPU systems So in the GPU land, this would look something like CUDA, and in the CPU picture, we want this to look basically something like OpenMP. So this is an object lesson in the temporary expedient becoming dangerously permanent. So when we put this in, we thought that the preferred GPU programming model would become apparent to us as the years went by, but I'm not convinced that question is still resolved. So we still have our temporary measure is still in there. It basically consists of for those of you who may not have done any GPU computing, I will say the view you take is one that you have broadly a host, which is the CPU, and then you are broadly looking to offload the computationally expensive parts of your problem, your kernels, onto the GPU. So, and you seek kernels, which usually mean loops in the OpenMP picture, and you want to express these as basically a function, which is this global, which has this sort of underscore global qualifier down here, and those so-called kernels will execute in parallel on the GPU. Traditionally, in the GPU picture, one has also had to explicitly manage your memory. So you have to make special allocations for device memory, which was historically separate from host memory. So all that is dealt with, and all that is really just a facade in the case that you are using the CPU, and just falls back to normal allocations. So when you're doing OpenMP, so this sort of launch my kernel. And on the host side is really saying, please just start me threads. So this basically injects OMP parallel into the code there. You need to do something else in the kernel to reintroduce work sharing in the OpenMP picture. So we have this extra thing, this for_synt parallel, which is basically a macro which expands to your OMP for work sharing. So that so this is a bit like if you're familiar with OpenMP offload, this is a bit like the two-stage process one used to start the kernel and distribute work in the GPU picture. But that so in threads that will, so we're basically looking here to write GPU-like kernels, but these will the work sharing gets done here in the kernel. Okay, so that should all allows us to run on both CPU and GPU if we have AMD or NVIDIA GPUs. This abstraction layer allows various other things, like if you need to do things like reductions. This basically looks like something like if you've ever done a manual reduction in OpenMP, you know you need some shared variable in which to accumulate your contributions to the sum on each thread, and you then have to synchronize and get your result back into the final picture on a single thread. So that's done here. So the interesting point, perhaps in context of ARCHER2, you'll notice there's some padding, which is quite important in this array. So if you, in the OpenMP picture on ARCHER2, so if you thought about just accumulating results per thread into an array, into the contiguous elements of a single array, you're in danger of what's called false sharing, where different threads are invalidating each other's cache lines all the time, and that is very noticeable on ARCHER2. So you have to basically introduce some padding into this array to make that work efficiently. So that's the sort of so-called target GP abstraction for the CPU GPU picture. The other element, which if you're familiar with GPUs, you've probably seen before, the thing you need to worry about for GPU computing is data layout. So separately within this code, there is a mechanism for switching the data layout around. So typically on the CPU, where one wants good caching behavior, you might choose, for example, if we had the three components of a velocity field in 3 dimensions, x, y, z, you might wish to store the three components contiguously in memory for one position and then position and so on. For GPUs, you want to do so-called structure of arrays, where you keep all the X components together and all the Y components and so on. So that's a separate consideration, but there's also some results concerning this. Okay. So some efforts at to see how this particular liquid crystal benchmark runs. Historically on ARCHER2, I found myself using prog-env AOCC, which had a small but noticeable performance advantage over the other compilers for this code. What I'll be looking at in the first section is just basically the performance at the level of one socket, 64 cores. And performance is going to be assessed by some figure of merit, which is basically just the volume of the system in lattice sites multiplied by the number of time steps divided by the time for execution, and also divided by the amount of resource, which is usually going to be per socket in this picture. So the actual numbers are also normalized by some volume factor. Okay, so here's a result, which is what I call generally referred to as saturation exercise. So there's a certain amount going on here. So I'll try and explain what is happening. So here we, on the horizontal axis, we have the problem size increasing to the right, and the vertical is our figure of merit. So up is good. And for each problem size, I've run a number of different exercises in this picture. I'll go on to discuss the details in a minute. Broadly speaking, what you see, if your problem size is very small down here on the left, obviously you're not doing very much useful work. As you increase the problem size, what one sees here is this goes up to some maximum point at which one saturates the performance, and then you reach this plateau. So in the limit of very large system size, one typically expects these problems to be memory bandwidth limited, and so you're just in the limit of large system size on the right. You're just maxing out memory bandwidth. The picture here in the middle, so what's going on here is one is gradually filling up L2 cache, and this point here is where the local problem size per core is just fitting into L2 cache. So that's your point at which you saturate, and after that you're basically out to main memory. So the details of the particular points here, we've got our two data layouts. This is array of structures and structure of arrays. There's actually not a huge amount to call between the two. I generally found actually structure of arrays was working, perhaps just had a slight edge on ARCHER2. The other thing I've done is to split up my 64 cores in different ways. So we have, for example, one MPI task, 64 OpenMP threads, or 2 MPI tasks and 4 MPI tasks. So again, broadly speaking, these are not so very different, but one could up here, just about the peak there, perhaps you could argue that the one MPI task is doing about the best job. So this gives us some confidence that our hybrid, our OpenMP implementation is working effectively under threads on ARCHER2. So that actually is not a bad result, and it's not a bad result effectively because we've written GPU kernels. So if you can write a halfway effective GPU kernel, what we've found is that this has generally meant you get a pretty effective OpenMP implementation as well. So the other interesting thing about this plot is just by running this on one node, this tells us something useful about what might happen to strong scaling if we started using more resource. So again, out here, if you think about doing a large system size out here on the right, if one then starts to try to chop that up and use more processes to attack it, one should hopefully stay up on this plateau until you get to this point here, where the local system size just fits in L2 cache. At that point, you start falling down here. So even if you had no MPI overheads at all, that tells you something about where your limit of strong scaling will be on ARCHER2, and that's actually quite a good. We found that to be quite a good guide. So there's a question in the chat, which is the saturation due to memory? Ultimately, here, yeah, as you're out here, you've maxed out memory bandwidth in this problem, yes. Okay, so One of the things, onto the things that didn't look so clever, for reasons which are lost in the missed time, we decided to have a look at a task loop in place of OpenMP4 in our OpenMP implementation. I think the hope here was that we could imagine trying to do some mixture of work in the sort of OpenMP task picture. So the first thing we wanted to think about is, could we replace our OpenMP4 work sharing with the task loop and not suffer any performance penalty? Well, the answer to that was, broadly speaking, no. So this is the same sort of result, just with these open symbols using a task loop in place of OpenMP4. Perhaps this is not too surprising in hindsight, as one really wants to, in the threaded picture, have some data locality in terms of which threads are operating on which data, and with task loop you lose that direct mapping which one has in a simple static schedule OpenMP4. Just to switch context here, so I've got some results here from an NVIDIA GPU. It should be said that this code is not at the moment compiling on ARCHER2 GPUs, so much for portability. But so we're waiting for ROCm 6 to get past that stage. So just instead, here's some data from NVIDIA. Instead, again, this is one GPU, and we're just looking at the saturation problem in terms of problem size, and this is our figure of merit. So if you were paying, if you were eagle-eyed and saw the figure of merit on the ARCHER2 was about 30 or so in these units per socket, the maximum on the GPU is perhaps 4 or 5 times that, which again, for this problem, which is memory bandwidth limited, if you just think about the peak memory bandwidth on these devices, the factor you would expect is about 4 or 5. So the results there, again, the details are, again, on GPU, you really do care about your data layout, so you better get that right for get your coalescing right. The different symbols here are just actually in the case where there is a non-cubic system size, they're just different sized slices in each coordinate direction, I think. So again, here, this saturation picture, because the memory, the GPU memory on this particular device is somewhat limited compared with ARCHER2, we can't actually saturate the performance, we'd say, in that situation. So there's the upshot of that is that in terms of strong scaling, if you take the largest system size you can get on a single GPU and try and chop it up and run on more GPUs, you immediately start falling down this slope, and performance will decrease on this measure. So that's basically telling you that there's no strong scaling available for this problem on GPUs, and you have to resort to weak scaling. Okay, so these plots varying the system size are quite useful to get at that sort of feature. Okay, so those were just a sort of view of the single MPI process or per node performance figures. The other important consideration we had in this work, thinking about hybrid, was of course the halo swap, at which point you need to exchange data at the edges of each MPI subdomain. And the problem you have here is in the hybrid picture, this halo swap is effectively serialized. So the question we wanted to ask was, can we use threads effectively to help with this business of the halo swap? So the other sort of approaches one might think about is, well, you could say, for example, could we imagine using MPI data types and things like that? You can do that, but that doesn't really give you a clear role for your OpenMP. So just in this context, to remind people, if you're running MPI and threads together, there is this level of thread support. So there's this MPI thread single, and these things you have to announce to MPI at startup. So this MPI thread single is just saying there's going to be no threading. MPI thread funneled is saying that the thread called MPI init is going to do all the MPI calls further on in the code, so that we believe that to usually think of that as being the master thread in the OpenMP picture. The next one down is serialized, which says that only one thread at a time is going to call MPI. And the most general case is thread multiple, in which more than one thread can be calling MPI at any one time. There are reasons probably to avoid thread multiple in the first instance, as if MPI has to make the synchronizations required to ensure that everything is thread safe, this means it's got to be very conservative, and so there may be performance implications just using thread multiple at all. So the picture we have favored is to use serialized or funneled, where the application makes the decisions about threads, and there's only ever one thread calling MPI. So just a little bit on the halo trick. As I said earlier, these are basically simple nearest neighbor halo exchanges. So if you have data at the edge of the domain, you need to send that in both directions at each interface. So the typical trick in lattice-based codes to do this has been to do each coordinate direction in turn. So if you send the messages in one direction, and then you can pick up basically the corners in the following direction, and so this means you only exchange messages in the coordinate directions. So that would be 3 sets of messages in 3 dimensions. The downside of this approach is that you have to synchronize after each coordinate direction, and it's that synchronization that we decided to get rid of in this work, and just bite the bullet and send separate messages in each different relevant direction to get the message. So in this 2D picture, we would send the corner data to the process that is diagonally adjacent in the decomposition. So the advantage of that is you have no synchronization related to this trick of each direction in turn. So you get more more messages. The code is more complicated, but you avoid this synchronization, which is, as you scale out, is potentially harmful. And I think, have I missed a slide here? No. Okay, so I think I have some results from that somewhere later on. Yeah, so the picture we ended up using here is this MPI thread funneled, and we have a picture which is something broadly. The classic approach here is to put out all your non-blocking receives ahead of time, and then what we're actually doing here is using OpenMP to share out the work of packing the data from the domain into a message buffer, and then we're just going to blast out an ISend for each message or each direction in the decomposition. And on the receiving end, what we ended up with is a rather simple picture where we just do MPI wait all to wait for all the messages coming in, and again we're using OpenMP to unpack the data back into the halo regions of the domain. So as just an example of this, we're now looking at strong scaling. So this is fixed problem size, and we're increasing the resource we're going to throw at this, and here's our figure of merit again up there. So a perfect strong scaling will be a horizontal line on this plot. So I think these figures represent an aggregate of a number of runs in which the errors were of the size of the symbols. So in terms of our halo swaps in the hybrid, the crosses here are the old halo where we were doing this synchronization in each direction, and the new desynchronized version does indeed give us a benefit, particularly at the point where you want to be, which is at the limit of strong scaling. So the other points on here, the MPI only are, this is the old picture of one MPI task per core, basically. So that is, again, that's broadly not competitive. So this using this hybrid approach, reducing the number of MPI tasks you're running does have a benefit for strong scaling in this problem. Okay, so if you're familiar with OpenMP, well, you may be wondering, well, could we do something better in terms of how we're using threads? So very sketchily, I've set out here some of the things we tried. One could imagine, for example, instead of trying to do this wait all on the receiving end and then unpacking all the messages at the same time, you could ask, well, can't we do something like wait for a message to come in and then unpack that one? And there may be a saving there in the messages coming in early, get processed well, and you have the ability to go back and wait for messages that are coming later. To cut a long story short, there didn't seem to be any benefit in doing that on ARCHER2, so there's one of the things that went wrong. And there are various things you could think about trying with this. You could think about, okay, can we do a variation on this where I want to use an OpenMP task to deal with the business of unloading the message buffer and still allows this more flexibility where I deal with messages as they come in. Again, we could not find any implementation of this which had any advantage, and usually it turned out to be slower. And you could try and even go the whole hog and very, again, in a sketch, try and use threads in parallel to process messages as they come in. Again, that did not prove beneficial in our experience. So we broadly just stuck with the MPI thread funneled approach for these. Okay, just perhaps in the last 5 minutes, I'll say something about capability day runs, which we tried for the, I think this was the first capability day back in last year, sometime earlier on last year. So what we wanted to look at here was the scaling out to large scale, and I've done scaling without, and then with I/O. So the other piece of work we did for this ECSE was to revamp the existing I/O mechanism in the code to use effectively MPI I/O. So the approach we take, we actually aggregate the data we need into a separate buffer using OpenMP, which gives us the possibility of doing asynchronous I/O, although we've not done any studies on that here. The other thing I'm looking at here, I've particularly chosen to try and stress the system by asking for output to a single shared file. The code does allow you to use multiple files if needs be, but I'm not doing that here. So this is the no I/O picture. Again, I've got a slightly complex set of results here. So here's our figure of merit again here, and we're out in number of nodes here. And I'm looking at a number of different system sizes. So there's some blocks of each of 3 sets of points. So that's the smallest system size, which is something like 128 lattice sites cubed. The red ones there are next system size up, 256, and so on to the largest problem there, which is quite a large problem. We don't run any production work of that size, certainly. So again, so within each group of 3 here, you're basically looking at strong scaling between the system size. This is effectively weak scaling, and again, a perfect weak scaling would be a horizontal line on this picture. So we're doing okay in this picture where I was stressing the strong scaling within a given system size. A good benchmark, of course, should include our I/O, which is this picture. So again, this is the same sort of plot. The results without I/O are the faint lines, actually, just as a guide there. So for the smallest system sizes, I/O is not having too much of an effect. As we move to the larger system sizes and the larger number of processes, the I/O here is having a catastrophic effect on performance. So there is a limit here, which I have found, to the effectiveness of I/O to a single file. So the answer there would actually have to be to go to multiple files for these system sizes. Also on these plots, we did both OFI and UCX transport protocols. There were some failures with UCX, but the OFI was generally more robust. Performance, again, much of a muchness between the two in the areas where it's sensible. Okay, so that's summary. I think I'll just let you read that and take any questions if there are any questions. Thank you very much. So there's a question about limitations of writing out results to file, and that there certainly are limitations there, and the effective bandwidth to disk you can get requires intervention in the Lustre file system and also in the MPI. I think I have a slide later on. So you need to be worried about your striping in the file system and various MPI I/O parameters, which controls things like the aggregation of the data between MPI tasks before they get written to the disk. But fundamentally, there is a limit to the bandwidth you can get to disk in this case of I/O to a single file. I think in those results shown there, which were on the Lustre disk system at that time, I think we were not getting more than about 30 gigabytes a second. On the NVMe file system, the same tests can get up to about 50 gigabytes per second to a single shared file. But for some of those larger system sizes out on the right-hand side of those plots, that's still just taking significant actual time. Hopefully that answers the question. So yeah, when I was talking about socket, I mean half a node in the hardware picture. So there's a question about bottlenecks in the cache. So the maximum performance of the kernels, the computational part of the problem, are controlled by the cache. Yeah. Output to disk is a question of bandwidth, aggregate bandwidth to disk in this problem. So they're slightly different concerns.
Okay, I see that there are no more questions. Yeah, we are like now 4 p.m. So thanks, Kevin, and thanks everyone for attending the webinar. Have a nice rest of the day. Bye for now.